Quantum computers will have become an integral part of scientific research across various disciplines. Their immense computational power enables scientists to solve complex problems that seemed insurmountable before. One particular field that has been revolutionized by quantum computing is materials science. With the ability to analyze and simulate the behavior of molecules and atoms at an unprecedented level, scientists can now design novel materials with extraordinary properties. Imagine lightweight yet incredibly strong materials, leading to the development of ultra-efficient and durable structures, vehicles, and even space exploration equipment. The impact of quantum computing will be felt across industries like energy, finance, and transportation as well. In the energy sector, quantum algorithms optimize power grids, leading to reduced energy wastage and more efficient renewable energy utilization. Quantum simulations help predict the behavior of complex systems, enabling scientists to design more efficient solar panels and energy storage devices. In finance, quantum computing's computational power allows for faster and more accurate risk assessments and forecasting. Stock market trends can be predicted with greater precision, reducing volatility and financial losses. Quantum encryption ensures secure financial transactions and safeguards sensitive data, creating a more secure digital landscape. Transportation will undergo a massive transformation, thanks to quantum computing as well. Quantum algorithms optimize traffic flow in cities, minimizing congestion and reducing carbon emissions. Self-driving vehicles become even more reliable and safe, as quantum sensors enable real-time analysis of the environment and efficient decision-making. And let's not forget about space exploration, where the advancements in quantum computing have paved the way for remarkable discoveries. Quantum communication systems allow for faster and more secure data transmission between Earth and deep space probes. Quantum sensors enhance our ability to detect exoplanets and study celestial bodies with astounding detail. The exploration of the universe becomes more vibrant and exciting than ever before. So, my friend, fasten your seatbelt and get ready to witness humanity's leap into a future where the impossible becomes possible, all thanks to the incredible power of quantum computing. Quantum computing operates on the principles of quantum mechanics, a branch of physics that describes the behavior of particles at the smallest scales. Unlike classical computers, which use bits to store and process information as zeros and ones, quantum computers use bits. Bits are quantum systems that can exist in superposition, meaning they can simultaneously be in multiple states. This is one of the fundamental features that gives quantum computers their extraordinary computational power. While classical bits can only represent a single state at a time, either 0 or 1, bits can represent a combination of 0 and 1 simultaneously. The superposition of bits allows for parallel computation, exponentially increasing the computational power of quantum computers as the number of bits grows. For example, if you have 2 bits, the computer can represent and process 4 states at once: 00, 01, 10, and 11. As the number of bits increases, the number of possible states grows exponentially. In addition to superposition, quantum computing relies on another phenomenon called entanglement. Entanglement refers to the correlation or connection between multiple bits, even if they are physically separated. When bits become entangled, their states become interdependent. Changing the state of one qubit instantaneously affects the state of another qubit, no matter the distance between them. This property allows quantum computers to perform highly complex computations and algorithms with remarkable efficiency. Quantum computing algorithms use a combination of superposition and entanglement to process information in parallel, leading to an exponential speedup in solving certain types of problems. It is important to note, however, that quantum computers are not faster for all types of computations. They excel in solving problems involving complex optimization, simulations, cryptography, and factorization of large numbers. Building and maintaining stable bits for practical use is a significant technical challenge in quantum computing. Quantum computing has the potential to revolutionize several fields and address complex problems that classical computers struggle to solve efficiently. Some of the key applications of quantum computing include: quantum computers can excel in solving optimization problems, which involve finding the best solution out of a large number of possibilities. This has implications in areas such as supply chain management, logistics, portfolio optimization, and traffic routing, where finding optimal solutions can vastly improve efficiency and save resources. Quantum computing poses both a challenge and an opportunity for cryptography. While quantum computers have the potential to break some currently used encryption algorithms, they also offer the possibility of developing new cryptographic techniques that are quantum-resistant. Quantum computing is driving advancements in the field of post-quantum cryptography. Quantum computers can simulate the behavior of molecules, enabling researchers to accelerate the process of drug discovery. By modeling the quantum interactions within chemical compounds, scientists can identify potential drug candidates with improved efficiency, accelerating the development of new drugs and treatments. Quantum computing can enhance machine learning algorithms by rapidly processing and analyzing large and complex datasets. Quantum machine learning algorithms have the potential to identify patterns, make accurate predictions, and extract insights that classical computing approaches struggle with due to computational limitations. Quantum computing can enhance financial modeling by efficiently processing large amounts of financial data and complex calculations. It can assist in risk analysis, portfolio optimization, option pricing, and scenario modeling, helping financial institutions make more accurate predictions and better informed decisions. Quantum computers themselves can be used to simulate and study complex quantum systems. This includes simulating the behavior of molecules, atoms, materials, and even subatomic particles. These simulations can lead to breakthroughs in understanding physical phenomena, discovering new materials, and advancing theoretical physics. While it is still an evolving technology, the progress made so far has sparked immense excitement and anticipation for the future possibilities that quantum computing brings. Developing quantum computers is a highly complex and challenging task. Here are some of the key challenges researchers and scientists face in the development of quantum computers. Quantum systems are incredibly delicate and prone to decoherence. Decoherence occurs when quantum states interact with the environment, leading to the loss of quantum information and the collapse of superposition and entanglement. This poses a significant challenge in maintaining the stability and coherence of bits, the building blocks of quantum computers, for an extended period of time. Quantum systems are susceptible to errors caused by various factors, including noise, imperfections in hardware, and environmental interactions. Developing effective error correction techniques is crucial for achieving reliable and scalable quantum computing. Error correction methods in quantum computing are intricate and require significant computational and physical resources. Building quantum computers with a larger number of bits is crucial for solving more complex problems. However, scaling up quantum systems is challenging due to issues such as increased vulnerability to errors, higher resource requirements, and integration difficulties. However, controlling and entangling bits becomes increasingly difficult as the number of bits increases. Developing efficient qubit interaction mechanisms that can be reliably controlled and scaled is a significant challenge. Creating and maintaining the necessary hardware for quantum computing poses challenges. Fabricating and operating bits with high fidelity, controlling environmental conditions to minimize interference, and integrating various components effectively require advanced technologies and expertise. Quantum computing experiments and prototypes are currently limited to specialized laboratories and research institutions. Providing broader access and connectivity to quantum resources for researchers and developers is a challenge that needs to be addressed for the wider adoption and advancement of the field. Developing efficient quantum algorithms that can take advantage of the unique capabilities of quantum computers is a significant challenge. Many classical algorithms need to be reimagined and redesigned for quantum systems. Finding practical applications that can benefit from quantum computing power and effectively mapping real-world problems to quantum algorithms is an ongoing research area. Superconducting bits. Superconducting bits are a promising architecture for scalable quantum computers. Several companies and research labs are working on designing and fabricating superconducting bits with improved coherence times and reduced error rates. Development of multi-qubit processors, such as the IBM Q System 1 and Google's Sycamore processor, demonstrate progress towards scalability. Efforts are being made to develop efficient traps and optimize ion qubit interactions, with companies like IonQ and Honeywell actively researching and developing trapped ion architectures. Photonic bits use photons as information carriers, making them highly resistant to decoherence and suitable for long-distance communication. Efforts are being made to develop advanced photon sources and detectors to improve the performance and scalability of photonic quantum architectures. Spin bits based on silicon quantum dots hold promise due to the existing infrastructure and expertise in silicon-based electronics. Researchers are working on developing silicon-based quantum devices with improved coherence and control capabilities, aiming for a scalable solution. Companies like Intel and Microsoft are actively working in this area. Some research explores the use of two-dimensional materials, such as graphene, for building bits. These materials offer unique properties that could improve coherence times and enable scalable quantum architectures in the future. Superconducting bits have their own strengths and weaknesses compared to other qubit architectures. Here are some key comparisons. Superconducting bits generally have moderate to long coherence times, although they are sensitive to environmental noise. Other qubit architectures, such as trapped ion bits or topological bits, can achieve longer coherence times due to their inherent isolation from the environment. Superconducting qubits have made significant progress in terms of scalability, with the development of larger qubit arrays. However, their scalability is still an ongoing challenge due to factors like crosstalk between qubits and maintaining coherence as the system size increases. Other architectures, such as trapped ion qubits or topological qubits, have shown potential for better scalability. Superconducting qubits have achieved high gate fidelities, meaning they can perform quantum operations with few errors. However, gate fidelities can still be affected by noise sources. Some architectures, like trapped ion qubits or topological qubits, have achieved even higher gate fidelities, making them attractive for error-corrected quantum computing. Other architectures may use different methods, such as laser manipulation for trapped ion qubits or electron spin manipulation for spin qubits. Superconducting qubits can be challenging to interconnect due to their fabrication complexities. Other architectures, such as trapped ion qubits, have inherent capabilities for long-distance entanglement between qubits, which could potentially enable better connectivity between qubits within a large-scale quantum system. Quantum error correction, QEC, is an essential technique to protect quantum information from errors caused by environmental noise or imperfect operations. Currently, the primary focus for QEC in superconducting qubits is on surface code-based architectures. The surface code is a promising QEC scheme that can detect and correct errors effectively. However, implementing surface code-based QEC in superconducting qubits is technically challenging due to several factors. To make QEC effective, a high-fidelity set of quantum gates is required. Implementing QEC in superconducting qubits typically requires additional physical qubits for error detection and correction. This poses challenges in terms of scalability and the need for higher qubit densities to effectively implement QEC. Reducing decoherence and improving coherence times is crucial for successful QEC implementation. As society embraces quantum computing, the world transforms into a place where unimaginable possibilities are realized. From groundbreaking medical advances to revolutionizing industries, the future becomes a realm of limitless potential. Quantum computing, the technological paradigm shift of our time, brings humanity to the cusp of unparalleled progress and discovery. Thank you for watching this highly detailed presentation. Please subscribe and like for future videos.